the details in terms of initiation or greater details in terms of processing and initiation would be from a protection module. But since you're just dealing with the introduction, we'll just touch on a couple of the key areas this afternoon. So we start by looking at the transducers. And why do we really need power system transducers? Simply put, and the standard is that once you're dealing with currents in excess of 200 amperes, then you can't directly, or you will not directly measure that current. So you need a transducer, which is going to reduce that current to a level that you can interface with. So simply put, by way of definition, your transducer is used for coupling either measuring instruments or relays when the current is too high to provide direct connection. All right, so the transducer is, if you for use of a better word, would be that intermediary. All right, so it's that component that is going to interface with the high current circuit or the high voltage circuit, and then the output is what we'll use for measuring, for control purposes. Yes. Now, key here is that once you introduce these transducers, you have to ensure that the information that you're getting on the output is a true reflection of what is on the system. And so when we delve deeper into transducers, we realize that, there are certain standards that will be applied to your transducers in terms of the level of error that will be involved. Some transducers we have to think about, and every time I go into this, I just touch base in terms of what you are now doing or what you have done in your magnetics, because we, delve back into some of that. Yes, but let me not stray from the main point. The key is here that you have to be able to represent or reflect exactly what is on the system. So we say that these transducers or measuring transformers, however we want to call them, must provide or must produce that scaled replica of the input. Yes, and so if you take it from the standpoint of measuring instruments for revenue purposes, yes, so in large facilities where, of course, the currents that you'll be experiencing will be way in excess of 200 amperes. The utility company, if the measuring instruments, if the transducers that are being used are not accurate, then either the utility or the customer will be robbed. Because if the error is such that you're not getting a true reflection as to what's on the system, then the utility may be getting more than what they should be. And two, which means that the customer is paying more than they ought to. And the reverse is true. If we are not getting that scaled replica, all right, or that accurate representation of what's on the system, then we can also have a situation where the utility is not getting what it ought to. So accuracy is important where measurement is concerned, because in terms of measurement, that is money. On the other hand, whilst accuracy is important, when we look at it from a protection standpoint, there are other implications. In other words, we are dealing with very high currents, and of course, once you have a fault on the system, although from our analysis, from the fault analysis that we have done so far, we have not considered the fact that under fault, the currents are no longer sinusoidal. So you don't just get a large, perfect sinusoid. You're going to get complex waves being formed. Yes. And the fact that you now have complex waves, it means that you also have harmonics. And then we go further. The fact that you have harmonics, it means that it may impact how the protection system may respond. As such, from a protection standpoint, we must be able to represent or accurately represent what is on the system, meaning whether it is sinusoidal, whether it is complex, whatever is there, it must be reflected at the output. And so we speak about measurement from a revenue standpoint, but we also speak about faithful representation of the waveform, yes, because that also has implications for how the relay, which receives this output, will respond. Okay? Any questions? Anything that I've said so far that is unclear?
Good evening, sir.
Hi, afternoon.
I would like to know up to when you have complex wave, up to which harmonic would it be significant? The surge voltage be significant?
All right. Well, that's a very difficult question to answer. In that there are certain harmonics that are present in a faulted wave that we use to differentiate whether we have a fault or it is just increased loading. And I'm trying to answer your question without delving too much into protection, yes? In terms of, let me just throw an example. In terms of, for example, protection of your transformers, there's a phenomenon that you would have looked at in machines known as Inrush, yes? Now, Inrush current has significant second and third harmonics. Now, Inrush is a natural phenomenon. So in that instance, we use up to the third harmonics. With me, Michael?
Yes,
so for those circumstances, we are looking for these harmonics, because we know that when we see these harmonics, it is really representing inrush and not a fault. But at the same time, harmonics may not necessarily be the best representation in terms of what we are looking for in a fault, and so we have to find other representations, and the one that comes to mind would be wavelets, which is well, I know it's a toolbox in MATLAB, but I'm trying to find a good definition for it. If you think about the Fourier transforms, where you're looking at a complete period, so you're looking at one complete cycle. For wavelets, what you're doing is looking at different portions of the wave. So whilst I mentioned harmonics, there are other considerations that needs to be looked at. So it's difficult for me to say, well, up to the fifth harmonic is what is important, because different harmonics tells us different things about the network. And also in terms of because in certain parts of the protection system, you may have a mix of capacitors, even though in large measure we no longer use wave traps anymore, but you do have them in parts of the system. And I may say in Jamaica we may not use them anymore, but you have mix of capacitors and inductors. And if you recall what we said when we were looking at resonance in complex waves, yes, that you can have resonance at one of these harmonics. And that now becomes significant for the power system because there are areas within the protection architecture that you're using capacitive and inductive components. And you want to ensure that under certain conditions that combination does not then create or be exposed or operate at resonance based on a particular harmonic. That's a very long answer to your simple question, which is, to what harmonic. But it is difficult for me to say up to the second or third, because different harmonics will have or cause different responses or have produced different concerns for your power system.
Yes, sir.
I know that is a long-winded one for your question, but please, I look forward to questions like this. All right.
Yes, sir.
Okay. So, as we were saying, the other issue in terms of faithfully producing replica of what's on the system. Let me just get my pen up. All right. The other concern is that in terms of your transducer, not only must it faithfully represent what's on the system, but here we're saying that your protection system may need to operate much faster, yes, or operate in a time that is shorter than the period of the transient disturbance. So or I know that yes, in terms of transients, we looked on the whole issue of damping, all right? And the type of damping will dictate how long that transient will be on the system, okay? So we're all familiar with that. What we are saying, and I know that, the questions that I may have given you networks to regarding transients, in many instances, the values have been arbitrary. Yes, the values have been arbitrary. And so the times that we have been working, that we have been calculating also can be considered arbitrary. However, within a power system, we're talking about when I say that a breaker takes 300 milliseconds to operate, or well, that's even too long. When I say a breaker takes 150 milliseconds, just the breaker, to operate, within the sphere of protection, that seems like a lifetime. All right, because we know are dealing with breakers that are operating in 60 milliseconds. All right, so that's the type of time we're dealing with. We need to be clearing a fault. We need to be clearing a fault within 200 to 300 milliseconds. And when I say clear, I'm including both the operating time of the breaker plus, the time that the relay senses and all of that. So the point we are making here is that the protection system may need to operate in a much shorter time than when the transient itself exists on the system. You with me? And so it's important that the transducer is able to faithfully represent what is on the system, because once that information reaches the relay, then the relay, based on how it is set up, will have certain decisions to make. And so we are dealing with a time-sensitive thing. You may have been playing around, you may have had even a 9 volts battery, and short circuit the terminals, and you would see the sort of arc that we are talking about. All right, that's a 9-volt battery. Now I want you to try and just expand your mind and think about, no, we're talking about 69 kilovolts, we're talking about 138K, we're talking about 3,000 amperes, 4,000 amperes. And if you don't want, if you don't want to even expand your minds to that, think of arc welding. Yes, that's just under 100 amperes. And if that can be used to melt metal in order to carry out your welding, yes, then you can understand that within a power system, we can't have those sort of currents in a short circuit on the system for very long. So it's important that the transducers faithfully represent this information so that the action that needs to be taken by the relay can be done without delay. Are we clear?
Yes, sir.
So there are certain strictures that are applied to your CTs, right? In terms of the errors that are associated. And as I said earlier, there are certain classifications that we will apply to our CTs. So you can't just walk in and say, well, you know, I have this level of current that I'm monitoring and I want a CT to do it. No, there's a lot more information that needs to be provided. Albeit, I tell you upfront that most of the equipment that you'll be interfacing with, whether it be your transformers, your power transformers, they come with their CTs built in, all right? But in terms of you as the engineer going out there, if you're gonna specify the purchase of a current transformer or a voltage transformer, then you would have to understand in terms of operation, what you need it to do, right? Whether it's just for measurement, whether it is for protection, and if it's for protection, what sort of error can you deal with? If it's for measurement, what sort of error can you deal with? So these things are important for your CT. Okay. All right. Where are we here?
Excuse me, sir.
Yeah.
So, sorry, so the CT would have been the so-called measuring instrument that relays the information to a relay. I think I asked this. I just want to get.
All right. The CT gives you a scaled replica.
Okay.
So the CT converts what is on the system to a value that is in a certain ratio, which comes to the relay. So in effect, it's not really measuring. It's converting what's on the system to a particular value.
Okay.
Yes.
Okay. Yes.
What measures the current on the system would really be your relay. So your CT is just producing the scaled replica, or your VT producing the scaled replica. In terms of measuring, which is where now we're going to process. Because remember, we spoke about detection.
Yes, sir.
So detection is really a CT. So it's detecting and providing scaled replica. The relay now receives that and makes decisions based on what has been received.
Okay, sir, understood.
Good. All right. Okay. So I've sort of touched on this already, but for transducers that produce your system current and voltage, for the current, it's your current transformer, and for the voltage, it is your voltage transformer. The primary of these devices are connected directly to the power system. And then the secondary, yes, which are standardized values. These values are standardized, and that's for convenience, yes, are then fed into your relay. And what are these standard values? For your CT, the standard output values for your CT are 1 and 5 amperes. Now, the 1 ampere was usually used in, well, based on the British standard. So you might find 1 ampere, yes, 1 and 2 amperes to be honest, from the British standard. So the BS standards would have your 1 and 2 and 5 amperes. The American standard, which is the ANSI standard, ANSI, the ANSI standard, the standard output for your CT is 5 amperes. All right, so the standard output for your CT, 5 amperes, that's the American standard. And for the British standard, it's 1 and 5. Okay, 1, 2, and 5. The 1 and 2, I just mention it because, yes, it's there, it has been there, but we hardly use it. So I suppose generally we can say that the standard output for your CT is 5 amperes. Okay. In terms of how we connect them, and I have sent you these figures already, so you can just refer to them. Yeah. For your CT, it's connected in series with the line or with your circuit, the power circuit. And of course, there are different types. What I'm showing you here is your bar type. Okay. And for your VT, well, obviously the fact that I have PT here tells you that this figure is a little old. But anyway, your VT is connected across. Now, the standard output for your VT is 110 volts phase to phase. All right, so it's 110 volts phase to phase.
Sir.
Yep.
Is that both for US and UK, sir?
Yes.
Okay, thanks.
Or 63.5 volts phase to earth, or line to earth. All right, so 110. Now, a voltage transformer, we're not going to get into it, but I think I did mention it last week in the introduction. I said that voltage transformers are very large. Right? In terms of cost, they cost almost as much as your power transformer. So whilst we were speaking about redundancy for your protection system, we said that you would not necessarily find the VT repeated, right? We'll have one set of VTs that's used in several areas, okay? Because they are very expensive and they are huge. So you'd have your VT there, giving you that standard output. And of course, you have CTs, let's just say, all over the place. Okay. In terms of actual, look at your VT, your CT. So what you have, these are your CTs here. All right. So those are your CTs. All right. These would be your bus bars. So this, what we are showing here, this would be an industrial setting. So those bars, or these bars rather, those would be your 3 bus bars. Obviously, it's a 3-phase system, yes. And so you have the CTs here, and the bus bars pass through them. So it means that the feed or the supply to this facility would all pass through your CTs. Now, what we are looking at here seem to be set up for measurement, all right? So the output of these CTs would then go to your meter, which would provide the measurement for revenue purposes. In terms of your CT characteristics, so what you would get when you purchase a CT, yes, and which you would use in your design circuit. You get the CT characteristics. And what I'm going to show you here, or the figure that you have, is a multi-winding CT. Yes. So it is a, let me see, let's just go to that. So it's a 1200 to 5 CT. What that means, yes, is that on the outermost winding, all right, which is there, what that means is that if we have 1200 amperes on the primary of the CT, or in other words, if we have 1200 amperes on the bus bar, right? So if 1200 amperes is being taken, then on the output of the CT, yes, you'd see 5 amperes. So in other words, if you then have 2400 amperes on the primary, then you'll see 10 amperes on the secondary, and so on. Any questions? All right. Now, I did say it's a multi-winding CT. So it's 1200 to 5. However, what that is also saying to us is that in order to get 1200 to 5, because you're using the maximum number of windings from the CT, it means that it will also give you the largest impedance. Yes? Question?
Yes, sir. I don't really understand the 2400 to 10, because if you have 100 to 5 and then you have 200 to 5, why is it would multiply the 2400 by 2? Or is it because you're using
No. What I'm saying, no, listen carefully. What I am saying is that on the 1200, remember this is a multi-tap. So you can use one of the 3, 6, 10, one of the 10 taps available. So if you are using the 1200 to 5 tap, you with me? If you are using that one, so if you are using the 1200 to 5 and 2400 amperes is passing through, then you'll get 10 amperes on the secondary.
Okay, sir.
If you are using, say, the 600 to 5, yes?
Okay.
If you're using the 600 to 5 tap, which is here, that's the 600 to 5.
Yes,
yep.
sir.
Then if you now have 2400 amperes on the primary, then you'll get 20 amperes on the secondary.
Yes, sir. Understood.
So it's a tap that you're using.
Okay.
All right. Yes, Ms. Montague. Ms. Montague, had your hand raised also?
Sir, I think her hand is raised from the start of the class.
Oh, okay. Ms. Montague, can you lower your hand, please? All right. Okay, so going back to what I was saying about the resistance, if you're on the 1200 to 5 tap, yes, because you're using the full winding, it means that it will give you the greatest resistance, which is 0.61. If you then use, if you're using the tap, the 300 to 5 tap, it means that you're using less of the winding. Okay? So what you have here is that it's 0.15. I mentioned this to you just for information, because depending on, we do have to carry out some calculations when using our CTs. And depending on the tap that you're using, then you'd have to find the corresponding resistance. Nothing for you to stress yourself over, at least not now. But we would use it for calculation purposes. So that's it. That's all I need to say to you for now. With in terms of the transducers, you have your CT. You know what the standard output is. You know, for your VT, you know what the standard output is. And of course, you know that you connect your VT in parallel with the system, your CT in series with the system. You have the figure there showing you a practical application. And of course, we have the characteristics, which gives us the secondary resistance and the winding. What these things up here, yes, it's significant, but that's for another time. Okay. So we now jump into relays. Now, I can talk to you about relays for 13 weeks, 4 hours a day, 4 hours a week. Yes? And I'll just talk to you about relays. Because there are just so many things that can happen in a power system that you need to be monitoring. So because we are only looking at, at the fundamentals of protection, what I'm going to do is just to talk about some basics in terms of not only how the relays work, but you know, there's just some basic principles surrounding your relays. All right, so here's my power system. I have my bus bar, yes, and we talked about bus arrangements before, yes. We just spoke about our CTs, right? And these would be our CTs. All right, so these represent the CTs. And what they are doing is just providing a replica of what's on the system. So you have 5,000 amperes on this bus bar, then the CTs produce, based on the ratio, it's giving a certain output to that relay. Here you have 32 kiloamperes. Again, this CT, right? Obviously, well, I shouldn't say obviously, but there may be a fault on the system. Yes. And you would note that you have 17, 6, 4, and 5. Those are all flowing into the bus bar. And we have 32 out. So based on what we see here, obviously we have a fault. Okay, so there's a fault on the system. Question is, you know, how do the relays operate now or behave in terms of clearing this fault? What you need to take note of is that you now have some, you have that, and that's an output, yes, to the from the CT. And you have a number in it. 5051. Up here, you have 5051. Okay. Now these are your relays. Now on your schematic, what you'll have would be your relay number. And so if you were to take up a schematic, a one-line diagram for your system, then you'd see all these CTs, or they wouldn't show you the CTs, but you'll see the relays, or you see these items with numbers in them, and they represent the type of relay that is being used. What we are seeing here would be overcurrent relays. But here in this figure, we are seeing 87, we are seeing 21, we are seeing 86. Well, we mentioned the 50 already. And all of these, yes, are the different relays that can be used on the system. The other thing I want you to also note is that on your system, you recognize these, all right? What do those look like to you? Anybody? What do those look like?
Transformers.
Transformers. So which transformers would those be? What do you think? It's coming to the relay. The relays. What kind of transformers would these be? Just take a while, guess. Come on.
Sir, step up to the...
No, not necessarily step up, but what kind of transformers? We have been talking about protection. It's the output of these transformers coming into your relays. What would they be?
Your grounded stars.
No. Maybe it's my
as in current transformer? Or
right.
voltage transformer?
Voltage transformers. These are voltage transformers. All right. Remember your current transformer, your CT, how is it connected in with the system?
Series.
In series. These are not in series, these are in parallel. So those are voltage transformers. Okay? And what you have here, this and that, those would be your CTs. Those would be current transformers. All right? Now, why am I mentioning these? Because these relays take in different outputs. Some relays only require current output input. Some relays requires only voltage inputs, while there are other relays that require both. Okay, so like your 87, your 21, 87 that would require your current input. Your 21 requires both. All right. So what we are saying is that within your system, you have these relays, and these would be in your relay house. All right. So these are in your relay house. The inputs to these relays will be coming from your substation. So you have your VTs, you have your CTs, yes, going in to your relay house. And then the decisions are made in that relay house. All right? Everybody with me?
Yes, sir.
Yes, sir.
So the question is, you know, what's a relay? So let's start there. Let's start with a simple thing. What are relays? All right? And simply put, it must produce keywords. It must produce a sudden, predetermined, yes, changes in one or more electrical output circuits when certain conditions are fulfilled. So in effect, yes, the relays are the brains of the system, but their brains are as effective as ours. In other words, they can only do what we have instructed them to. Right? So they are going to produce sudden, predetermined changes, right? And these are what we then refer to as the decisions that the relays make. So they are going to decide what will happen based on a particular input. So if the current, and we're going to talk a little about overcurrent relays, but if the current goes above a certain value, the relay knows that it must operate. Still yet, if it goes above a certain value, it knows that not only should it operate, but it should operate with a particular speed. So if the current is X times the setting current, then it's going to operate at this speed. If it is 10 times, then it's going to operate, you know, maybe faster. If it's 15 times, it's still going to operate even faster. Right? So these are the predetermined changes that the relay will make. Are we clear? All right. Now for your protection relay.
Why is it that it doesn't just operate at one standard quick speed? Because we're trying to minimize the amount of time before the fault could spread. So why not have like a very quick time for every speed?
All right, that's a very, very good question. However, think about it this way. The fact that a current has gone beyond a predetermined value does not necessarily mean that there is a condition that requires system separation.
Okay, sir.
A classic example is there are times when you have to transition load. So you're doing switching, right? So And if you recall, when we were looking at the bus bar arrangements, one of the things we looked at was whether or not, you know, they were maintenance friendly. So sometimes if you're going to maintain a certain type of bus bar arrangement, you have to take off all the circuits. If you just want to look at one circuit, you know, you have to switch off everybody. Now, the switching exercise that can take place may mean that you have to move a particular group of customers to a particular circuit, do what you have to do quickly, and then switch them back. Or, you know, so in switching operations, you may have to do that. In doing so, you may end up causing the current on a particular feeder to go beyond what its normal maximum is or should be. You with me? Now, you don't want the system to shut down because you are carrying out that switching operation. So whilst the overcurrent relay will detect that, yes, the current has exceeded the value that it ought to, or exceeded this predetermined value, it will react slower to that overload. With me, Ms. Michael?
Understood.
Good. And then when you have it, you know, worse, then it acts faster. And when we look at the characteristics, you may get a better feel of what I'm trying to explain here. Okay? For your protection, now, remember we said here that there's a predetermined change that will be made. That change can also include sending an alarm, because there are some relays in the system that their purpose, their initial purpose, is to alert the utility that there's a problem, or there's a potential problem, or there's a problem on the horizon. Yes? So it's not always that when you have an issue, you're going to shut down the system, because, and this is something that I try to emphasize with protection students. The main purpose of the power system is to provide electrical energy to customers. If the utility isn't selling power, if people aren't using electricity, they cannot make money. So you don't want to take people off the grid unnecessarily. All right? So at all times, the main objective is to maintain supply. Okay? So in some instances, what happens is that you're warned, you get a warning. If the warning isn't heeded, then it escalates to separation. All right. So for your protection, you have disconnection primarily, but you also have cases where it simply warns. All right, because you really want to minimize the number of customers that have to lose power. Very important. Never forget that. All right, you're going out there as electrical engineers, especially for those who are going to find themselves in the power industry. If you end up in the power industry, understand that your purpose is to provide safe, reliable, continuous power. At the heart of what you do is to ensure that customers have power. All right? Okay. So these are your types of relays. You have your electromechanical, you have your static. And, you know, a couple of years, the SCL, this was your business. That's where we had transitioned to. These are some of the relays that are used a lot currently in JPSCO. This is where we are coming from, right? Well, for me, I have struggled both. So we have the electromechanical and we have the static. For you, you would have, well, most of you would have moved from, some of you would have seen the watt-hour meter, the one with the rotating disc. Some of you may have seen that. Some of you couldn't, if not cared less, really. And so you would have just moved from the standard digital meter to the smart meter that we are now using. All right. But I mentioned that because this electromechanical, the principles on which it is based, the operating principles on which it's based, is similar to the watt-hour meter. So if you're familiar with that meter, then you would understand how the electromechanical works. And everything that the electromechanical can do have just been upgraded and subsumed into your static relay. All right. So in terms of the relaying elements, you have your attracted armature, your moving coil, your induction cup, your thermal elements, you have motor operated elements, you have mechanical elements. So these are the elements that are utilized in your electromechanical relay. All right. Just as a quick example, the next figure that you would have had, that you have in what I have sent you, is the example of an attracted armature. Yes. And I use this one because it helps to provide clarity on the contacts that you would see. You know, we mentioned, you know, normally open and normally closed. Yes. And as I said, I use this particular figure because it helps with explaining those two contact types. All right, do we have this? Can I move on? All right, silence means consent. All right, so for the okay, for the attracted armature, just note the contact. So you have up at the top normally open and normally closed contact. And what that means, a normally closed or the name given to a contact is the condition when before it is energized. All right. So, or the unenergized state of the contact. So without any action on the contact, the normally open means that it is open. And normally closed means that it is closed. So when the magnetic pull on your armature is such that you then get movement on the arm, right? So you then get movement on the arm upwards because you are then pulled in, all right? The normally closed would then open and the normally open will then close, all right? So this gives a simple illustration for the operation of an electromechanical relay. Okay. I said earlier that the principle is similar to that of the watt-hour meter. Yeah, I found some old watt-hour meter figures. Any questions regarding this attracted armature? I mean, it's quite simple. There's nothing fancy about it. For your watt-hour meter, you have your turning, your disc. Yes. You have the principle is that you have fluxes which are superimposed on this disc. One flux is as a result of the current, yes, and one as a result of the voltage. So you have the voltage producing a current, which produces a flux, which is superimposed on the disc. And for the current, it produces a flux that is also superimposed. And then, of course, they cause the disc to turn. The greater that flux, the faster the disc will turn. So in other words, if you have more current, because for the voltage, that will be fixed. Yes. So as the current increases, it means that that flux will increase. Yes. And so the disc, the torque on the disc will increase. All right. Figure out much better, but there are a couple of things that I'm better able to show you here. Unfortunately, we are not in the lab where I can, show you the physical relay. But a couple of things I want you to note and just keep in the back of your head when we go further in the lecture. Up here, all right, is what we call the time dial. And if you note, you have some numbers. So that's 1, 2, 3, 4, 5, 6. All right. So you have numbers there. And of course, you know, that's graduated. So that's your time dial. Below your time dial, and you know, this, it would really help if we had the physical thing, but right here, that's your movable contact. Yeah. So that's your movable contact. And here, that's your counterbalance spring. So the movable contact is on top of that spring, and all of that is connected to your disc. So as the disc rotates, then it will move the contact. All right, so it will move the contact. Now, once you know the input is removed, then the contact will return to its rest position. All right, so this thing here, I think I am messing it up now, but that's your movable contact. So it is moving from over here, and it comes around, and it comes to the fixed contact. Now, if you note carefully, I don't know if you can see it clearly, but if you note right here, all right, that is the fixed contact, and it is actually fixed by the time dial. So when I turn the time dial, what the time dial is doing is actually moving the fixed contact further away or closer to the movable contact. So depending on the time dial that I'm using, all right? So if I were to turn the time dial, the lower the number on the time dial, it means that the fixed contact would be closer to the movable contact. Because remember, as I said, the rest position is over here. Are we clear with that? So if I had it at 1, it means that the fixed contact, which is that little area there, the fixed contact would have been closer to the movable contact. So the lower the number on the time dial, it's the closer that the fixed contact will be to the movable contact. Or in other words, the faster the relay will operate. So the lower the time dial number, faster the operation. Lastly, up here, and I have it highlighted as the plug block. Now, we call it plug block because what we have here, let me just change the color. What we have here, that's your plug. Good. And what you have here are some holes or openings. Now, these openings, each of those openings has a number written on it. And that number represents the current or the setting current for the relay. And so in order to select one of those numbers, you simply remove the plug and insert it into one of those openings. So you'll take your plug and you'll put it over here. That may represent 1 ampere. So it means that once it hits 1 ampere, yes, it will start operating. Or if you put it into 3 or 3.5, it may be at 4 now. So what that is saying is that the current into the relay must reach 4 amperes before the relay operates. Any questions? I know I'm going rather quickly, but any questions?
Yes, sir.
Go ahead.
I notice you're saying like 1 ampere, 2 amperes, but you're saying that the relays would have seen the actual current or voltage. Well, current in this case, but yet we're still working with the smaller scale values.
Yeah, but remember, what I said about the plug block is that that is the current at which the relay will operate. Never forget what we said here. All right. So in other words, what we're talking about predetermined. So in other words, we have determined that the relay will operate when it sees 2 amperes or 3 amperes. Okay?
Okay, sir.
Now, that determination is based on what we select up here. So that's what we call the plug setting. So the plug setting, which is also referred to as the tap setting because really, when I select one of these, all I'm doing is tapping off a winding. So it's a long winding, yes? It's a winding in there, and each of these points, each opening represents me tapping off a portion of the winding.
Okay,
all right?
sir.
So we're going to talk a lot about taps. You have taps for your CT, we have taps for the relay. So your plug or your tap setting is really how you set the relay in terms of what current it will operate at. So that will be part of the so-called predetermined operation for your relay.
Yes, sir. So in essence, the relay does have that, what you would say now, like transmission or experiences that kind of that level of high current, but it is set to operate at 5.
Tell me
or
what you mean
1.
by high current.
Meaning like, because as you said, the relays are connected to the
CTs,
to the CTs. So, oh, okay. All right. I see where I'm getting it wrong. The CTs give the relay that the
Output.
scale values.
Exactly.
Yes.
So what is on the system is not what comes into the relay.
Yes,
It is the replica, the scaled replica produced by the CT that comes to the relay.
Yes, sir. Yes. Thank you, Dr. Isaacs.
That's why I'm here.
Sir,
Yeah.
sir, this is so because, like, for example, to build a relay that will work directly with, which is with what's on the system, so it would be more expensive. That's the reason
You
why.
can't build it. You can't build it. Because think about it. If you have a relay that is going to take 600 amperes, think about, and let's come back to some basic electrical principles. Current carrying capacity, yes, is reflected in terms of from a conductor standpoint. The current carrying capacity dictates what? What does it dictate?
The amount of current.
No, for a wire, what does it say about the wire? The capacity of the wire to carry a current is based on what? What about the wire?
The material and cross-sectional area.
The area, the size. So the size of the wire. Good? Now,
yes, sir.
for voltage, for your wire again, what does that dictate for your wire?
The material, sir.
What do you mean by material?
The type of conductor, sir.
What do you mean by type of conductor?
The distance.
Huh? Voltage dictates insulation. Insulation. So if you think about a piece of twin on earth, all right? A sheeted cable, yes?
Yes, sir.
What do you see written on it? By the way, I'm assuming everybody know what a twin on earth sheeted cable is, but it's that you have the 2 black wire and piece of copper inside there in a white sheet. What is written on it, if you can recall? Tell me what is written on the outside, on the white part. Anybody? Who was that?
Mr. Thomas.
You're breaking up. You're breaking up. I'm not hearing you clearly. Yeah, Mr. Thomas. All right, type it for Mr. Thomas, because I'm not hearing you. Just type it in the chat. All right.
So normally we have written on it, so it's like the cross section on here, sir.
No, sir. You type it, Mr. Thomas? All right. Anyway, in the interest of time, what is written on it? Oh, I think he just typed it. Let me see. Not the size, not the size. What you see written on it is the voltage. You see 500 volts or 600 volts. All right. What that is saying is that that is the safe working voltage for this insulation. So it's giving you the rating of the insulation. So come back to the question that Mr. Adams asked. In effect, for me to build a relay at that size, yes, it will be bigger than the relay house. Because I have to deal with the insulation, I have to deal with the current capacity of the components. Yeah? So we spoke earlier to the need for standardization. So we are able now to standardize the output of the CTs at 5 amperes. So I know that my relays would work up to 100 amperes. But we'll come back to that. I don't want to confuse the situation yet. All right, for your static relays, these are the type of elements that are used. No, where we are now, it's primarily microprocessors. Yes, nothing significant about that. We know that's where we are. So you go into a relay, this is what you would see. Okay. All right, so talking about relays, your protective relays analyze key quantities. So they are looking at voltage, they are looking at current, and of course, derived quantities such as power and impedance. So I can have a relay that is measuring voltage. I can have one that is measuring current. I can have one that is looking at power, impedance. Remember when we looked at I think that's what we started with. So we talked about the wild power system with all that can happen, and we talked about the loss of power. And in other words, there are so many things that can go wrong in your power system, and you need to be able to know that it is going wrong and be able to do something about it. So you have these relays which use different inputs to make certain decisions. Okay, folks? So we have magnitude relays, which are just you looking at how large the voltage is or how large the current is. And we're going to look at the overcurrent relay in a short while. All right, so we have magnitude relays, which looks at the magnitude of the current, the magnitude of the voltage. But you also have relays that measure voltage, but in measuring voltage, it is calibrated in frequency. Why? Because the frequency and the voltage are connected. So we know that with certain deviations from voltage will affect the frequency in a particular way. All right. Again, well, it is something that we would have mentioned in power systems analysis, not necessarily what you have done, but it's referred to as the droop characteristics. So we look at that for our machines. Yes, and we know that based on the output voltage, then there's certain things that are happening as far as the frequency is concerned. Okay, so we are measuring voltage, but we have it calibrated in frequencies. So those are your magnitude relays. Just looking at how large voltage is, how large the current is. Okay, then you have product measurement relays, which is similar to what we mentioned earlier, the watt-hour meter. All right, so it's looking at two fluxes, one produced by the current being taken, one produced by a current which is equal or equivalent to the voltage. All right, and the interaction of these fluxes will cause your disk to turn, and the torque, yes, is based on the fluxes. So I increase the current, I take more from the supply, then it means that this is going to turn faster. I reduce my consumption, it slows down. But of course, there's a balance, you know, because we're talking about overshoot, and we're also talking about, well, I shouldn't say overshoot, I should just say momentum, right? Or not momentum, but inertia. So in terms of when it's going quickly, yes, when you stop that, yes, it's going to overshoot a little, but at the same time, when you move from low consumption to increase your consumption, it's going to then delay slightly. So it balances itself out. But today we don't have to worry about that because we all have digital meters. Okay. So again, you know, just re-emphasizing the watt-hour meter. So this would be the mathematical relationship between the two torques. So the relay, we can have it so that it will respond to any two quantities. Okay. And as I said, you know, we can, this can be based on calculating or determining power. In our case, energy. Yes, because the watt-hour meter is really measuring energy. But we can extend that to any two quantities of the same frequency. And it comes back to our knowledge of phasors. You know, we can't add two phases unless they have the same frequency. In the same way, we can't multiply these fluxes unless some have the same frequency. Okay? So we have magnitude. We have product. So obviously, we're going to try ratio. Right. And I'm gonna look briefly. It's now 4:15. We're gonna look briefly, as I said, on the magnitude relay. You know, that's the one we're gonna do a little calculations with. But you know, just to say that you have the product and you have the ratio. Now, I'm not sure we have been able to do it as yet, but we can to develop torques that represent the quotient of two quantities. Maybe a bit of a challenge. All right? That may be a good major project. Hey, who to tell? We are into innovation here. But if we have the forces exerted by two windings, all right, and these forces are proportional to their exciting currents, then this relationship would be true. All right. When balance is achieved, it means that the two forces would be equal. So we have them being exerted, yes, on two windings, the force exerted by two windings, sorry. All right. And this principle is what we call the balance beam principle. So the two forces, when they are equal, would establish a balanced beam. Okay? So we have it exerted at either end based on the two coils. When balance is achieved, this is true. which means that the ratios of the two currents would be constant. Or in other words, that would establish balance. So A over B is equal to some constant. Now, once you have a departure from this balance condition, it means that you need to operate. Going back to the original principle, that the relay, yes, have these predetermined conditions for operation. So you have the balance, IA over IB is a constant. Once there's deviation, it means that you need to operate. All right?
Sir, can you go back for 2 seconds, sir? Thank you, sir.
You're welcome. So within a certain range of values, what we are saying is that the ratio, and this is important, it is the ratio that when exceeded that will cause operation. It isn't the actual values, it's the ratio. So A over B is a constant. If that ratio is violated, yes, within a certain range, if it's violated, then operate. That's what the relay would be set up to do. And we use it for impedance relays. Of course, the mere fact that I mentioned that, what it is saying to us, impedance is what? Voltage over current.
Yes, sir.
All right.
So it gives both current and voltage, sir, in its
exactly.
operation.
Exactly. So an
So
impedance relay. Huh?
It would be like a 21 relay, so you're talking about.
Yeah, it sounds like you have some previous knowledge. Yes, that's a 21. That's an impedance relay. All right. So it will have a voltage, a VT input, and a CT input. Yes. And it looks at these two, compares them, and once the ratio is below a certain value, it operates. Because the comparison that it makes, if you have a specified voltage over current, it means that it will give you a specific value of impedance. Once it changes, because normally, yes, normally, when you have that fault, the current is much larger than the voltage. So the increase in current will be much larger than the voltage. As a matter of fact, the current will increase, and in most instances, the voltage will be lowered. So what you'll have is that the impedance would then be smaller than the preset value. So the impedance relay operates on the principle that once the impedance falls below a preset value, it should operate. All right. Okay. So as I said earlier, we want to spend a little time looking at the overcurrent relay. All right. And just, run through a little exercise with it. So for your overcurrent relay, we have already established that your current transformer is the input to your overcurrent relay. And overcurrent here simply means that it will operate once the current, the preset current is exceeded. All right, but it is not a straight operation in terms of what comes in. But yeah, we'll go through and we'll see how this works. Remember, I used two terms earlier when we were looking at the block. The block. We had said what? We called it plug. What else did we call it? Anybody?
Tap
Tap something.
All right. So we said plug or tap. Note what we are calling it here. Pickup. So I can use any of those three terms, and I'm talking about the same thing. So it's either tap, plug, or pick up. Okay? Enough said. Don't have to go over that one. So the magnitude of your current, if it's greater than the predetermined pickup current, then the relay contacts will close, and it energizes the trip coil for your circuit breaker. All right. If it does not reach that value, it means that the contacts will remain open, and the trip coil will not be energized. All right. So again, go back to the diagrams that I sent you earlier, or I sent you yesterday. I hope everybody had access to them and you're following me with these. All right. So for the overcurrent relay, all right. So here's my CT. By the way, those dots that you see there, those are the polarities for your CT. We're not getting into that today, but just in case anybody was wondering, because I think I have shown it on a number of figures without commenting on it. So that's my CT, okay? This is the secondary current for your CT. So this is what is actually on the system. Whatever that is, I now get I prime, that is the output of the CT, and it goes into the relay operating coil. All right, so it energizes the coil. Here I have a normally open contact. All right, so if the current exceeds the predetermined value that I have set for my relay, if it exceeds it, then this contact will close. If it closes, it then energizes the breaker trip coil. Note that the relay does not produce an output to the contacts of the breaker, because the contacts of the breaker carrying a couple hundred amperes. Yes? So what it does is to send it to a trip coil, which operates a trip circuit in the breaker. And then that trip circuit would operate the breaker. So the relay does not send output to the contacts of the breaker. Please, please, please. All right. But then again, you know, it's not something that I would be stressing for you guys, but just for your information. So key here, students, key. You see this? That is a separate supply, usually your batteries, that are housed in your relay house. Why is that important? Okay, you're protecting the system. You don't want to be depending on the system that you have to protect to provide you with power. You with me? Because if there's a problem on the system, that then renders the transformers in the substation inoperable, and you're depending on that for power to operate your relays. When you have a problem, you know, you're really going to have a problem. So simple things like battery maintenance. And I may have told you the story about someone who, you know, well known to us, well, to some of you at least, one and two of you, whose job it was to maintain the batteries. And we ended up having an all-island blackout. Why? Because the batteries at a substation were not maintained. Right? So as engineers, we can't overlook what you may call the simple things. But anyway, I digress. So here is the operating space for your overcurrent relay. Once the current is below a certain value, then it is blocked. Once it's above a certain value, then it trips. All right, so anything outside here should cause it to operate. And let me say operate, right? Because this is the relay. The tripping really takes place on the part of the breaker. All right? All right. So coming back to what Anaki had asked earlier, The time delay overcurrent relay responds, yes, to the current magnitude, or there is an intentional delay. So there are overcurrent relays that once they are asked to trip, or once they reach a threshold current to trip, there is a specified amount of time that is built in to say, you know, wait and then trip. So you wait 10 milliseconds, then trip, right? So you have that.
Sir.
Yes.
Sir, is it that for this time, sir, if the current go back to the block, the magnitude that, yeah, yes, sir, will it
will reset?
Okay, okay. Thank you, sir.
Yeah. And this time delay, so now we're dealing with inverse. I'm trying to reel in a lot of the information, but anyway, you're going to hear it. So for these relays, the primary one that we use is known as an IDMT, right? It's an inverse definite minimum time. So the timing on these relays will be dependent on the magnitude of the current. All right, so the higher the current, the faster. And then the third point I want to make, and please, students, write this in red. And after you write it in red, circle it. And after you circle it, underline it. Because I have been saying to you from we started mentioning overcurrent that it operates on pickup, yes? And I was deliberate in doing that. However, what the relay is set up to operate using is multiples of pickup. Multiples of pickup. So in other words, if the pickup current is 3 amperes, in terms of the operation of the relay, if a current of 18 amperes comes into the relay, yes, it will be 18 divided by 3 to give you 6. And this is a 6. This 6 represents multiples of pickup. And I'll show you that in a few seconds, a few minutes. Just take it from now. Just take this from now. So it operates based on multiples of pickup current. Are we clear? All right. So coming back to the operation, in the block region, what we are saying is that in terms of the time, yes, with the current being all the way out here, in terms of magnitude, it means that TD1 is much shorter, or not much, but shorter than TD2, and TD2 is shorter than TD3. So in other words, the closer it is to the block region, is the slower it will operate. Okay. Are we clear? All right. Am I here alone? All right, cool. Let's move on. So we have some characteristic curves, and it's a plot of the operating time against the relay input. And this relay input is in multiples of tap. All right. There's also the current tap setting and the time dial setting. Remember that thing that I showed you that you have to turn to determine how fast the relay operates. And the lower the number is the faster it will operate. So for the same current, if I have it on time dial 1, it means that it will operate much faster than if I had it on time dial 5. So the lower the time dial, the faster the operation. Okay? All righty, so going back to the figure, so I set the time dial and I set the plug. So those are the two settings that I would have for my relay. We're not going into relay setting now. That's not something it's not on this syllabus. So what I want to know highlight would be the curves. All right. Remember we said you have the time dial setting, and everybody have this figure, right? I did send it, so yeah, you should have it. So you have the time dial setting. Note starts this one, the CO8. This is just the name of the relay, all right? So the CO8 relay, yes, starts from 0.5 and then 1 through to 11. Over here is the operating time, and note it is in seconds. If you recall that paper I sent you last week, you would have seen this figure on it in question 4. Okay? And then down here, and this is a Lin log graph. So down there, we have the multiples of tap. So multiples of tap. So down here, multiples of tap. Up here, time in seconds. Here, we have the time dial setting. And over here, we have the tap settings. All right? So we have the tap, we have the time dial, and we have the multiples of tap. All right? So I'll keep this. Well, you have the figure. Is there anyone in the room without the figure? All right, so we can move on. So here's a quick question. The current, the secondary current of a CT to an overcurrent relay, first of all, is 5 amperes. And we want to use the characteristics to estimate the operating time of the relay if the tap setting of 8 and the time dial setting of 1 are used. We ready? You don't have to write everything here. Let's just go through. So for 5 amperes, remember now when using a time dial setting of 1, all right? So if we're using a time dial setting of 1, it means that we are on this curve. All right, so we're on the second curve. Body with me? All right, so let's start with the first one. If I have a current of 5 amperes, so if I have a current of 5 amperes, how long would it take for the overcurrent relay to operate? Do I need to call on persons here? Mr. Leon? Mr. Leon? Mr. Leon not here? Okay. Next, Mr. Finley?
Yes, sir.
Yeah, come talk to me. We have 5 amperes from the CT. How long would it take for the relay to operate? Look at the figure. Look at the operating characteristics. Huh?
The time dial setting was 8. That what the question said?
I said the tap is setting. The tap is 8.
Around what, 3.2 seconds?
3.2 seconds. All right. Let me see now. Miss Downer, what you say about that? You agree with him?
Sir,
Yes.
with the if I agree with the 3.2, sir?
Yes, man. That's yes or no. Just tell me yes or no.
I'm not sure, sir.
Okay.
Because
Yeah, man, tell me. Just tell me. Just tell me your thoughts.
sir, I'm not understanding the usage of the values, sir.
Okay.
Because he said
Tell me what you don't understand.
Sir, he said the time dial is set at 1.
Yeah, man. So it means that we are using this curve.
Right.
Where am I? We're using this curve.
Right.
So we're cool with that.
Right.
Mm-hmm. Next.
And then he said the tap is at 8.
Mm-hmm. So when we have 5 amperes coming in, how long would it take the relay to operate?
3 seconds.
5 amperes.
Yeah, man. There are 5 amperes coming in. So how long would it take the relay to operate? He said 3.2. Do you agree with him?
Yes, sir.
Okay, I pressured you into that one. My apologies.
Sorry, 0.3 seconds, sir.
You said 0.3.
Retract my answer.
Oh, you retract. Okay,
Yes,
all right. 0.3. All right.
Sir, I'm not.
Sorry.
No, Mr. Venner, hold on. No, man. All right. In the interest of time, is there anybody apart from Mr. Venner and Mr. Sinclair who disagree? Whether disagree with the 0.3 or the 3? Yes, Mr. Dwyer.
Yeah, me that's a 1.6, but I'm not sure.
Yes, sir.
Mr. Thomas has a 1.6 too?
Yeah, with the top divided by how much current we're expected to
No,
use.
sir. No, sir.
Well,
I'm not sure.
Okay. All right. Any other disagreements? Nobody?
Sir, I would say 0.3.
You said 0.3. So you agree with Finley? You agree with
0.35,
Finley?
sir.
What I?
Yes,
You
sir.
said 0.35. Oh, you're a little more accurate.
Yes, sir.
Nobody else? No dissenting voice? So Shirley, what you say?
I agree, Mr. Finley, sir.
I agree with Mr. Finley.
Sorry.
Mr. Venner, no.
Oh.
I'm not tell anybody apart from you. Yes, Miss Michael, what you say?
Sir.
Yeah.
8, sir.
Yeah.
It's a multiple of the pickup current, right?
I don't know. I just.
So I'm like wondering after his first graph and you said it's 0.35, if we're supposed to divide by 8 in order to get.
No. What does the 8 represent? I'm happy that you're thinking. What does the 8 represent?
The tap setting.
What that mean?
That's the operating current.
That's the current at which the relay operates.
Yes, sir.
So if 5 amperes come, will the relay operate?
No, sir.
Good. So the relay will never operate. Everybody clear now? If 5 amperes is coming to the relay, the tap setting of the relay is 8. Okay? So if the tap setting is 8, it means that with 5 amperes coming into the relay from the CT, the relay would never operate.
Okay, sir.
Good? All right. Now,
Yes,
next.
sir.
So if you say you understand that, next one was 10 amperes. So if 10 amperes coming from the CT, and we have to hurry up because I messed up my timing. But anyway, with 10 amperes coming in from the CT, How long would it take the relay to operate?
0.2 seconds, sir.
Huh?
0.2 seconds, sir.
Or you get 0.2? Quickly, no man, just tell me you get 0.2.
Sir, if you go across on the center top graph to 10, sir, you go to meet the curve, which is at 1, sir.
Okay, so that would be 10 amperes, right? But the 10 that you are referring to, Mr. Smith, what does it represent?
The center top setting, sir.
No, sir. Read the graph. What on at the bottom of the graph? Wait, sir.
So the relay input current in multiples of current top settings.
Exactly. So 10, as you have it there, would not be multiples of top. 10 amperes. So the multiples of top would have been 10 divided by 8 because the top is 8. So what is 10 over 8? What is 10 divided by 8, people?
1.25, sir.
1.25. This would be 1.5 right here. Agreed? Everybody agree with that? Come on, man. We have... Yes. So therefore, 1.25 may be somewhere down there. Yes?
Yes, sir.
Yes, sir.
So the only
Yes,
answer
sir.
you could give is that it would operate in excess of 6 seconds. Because you really don't know. Don't worry. I don't want you to feel good or bad about this thing, you know, because you're just learning it. So there's nothing wrong with getting it wrong. And I really appreciate those who have gone out on the limb and at least give me a response. You with me? So don't get worried about getting it wrong. That's not, it's neither here nor there as far as I am concerned. All right? I'm just happy that you are willing to give a response. So at 24 amperes, what will be the multiples of top? Come back to me, Mr. Smith, since you say you understood what I just said.
Yes, sir.
At 24, what's the multiple of top? Mr. Smith, where you going?
Yes, sir. You can't get 24, sir. Would that be 24 divided by 8?
Which is?
3, sir.
Good. So what is the operating time?
So that would be 0.8 seconds, sir.
Beautiful. You realize we all get it now? This is the beauty, students, of getting it wrong. Getting it wrong and learning from your error is how you improve. You with me? Don't be afraid to get it wrong. Just don't get it wrong more than once. So at 120, what will be the multiple of top?
15.
15. So at 15, what will be the operating time on time dial 1?
That look like 0.3, sir, or 0.2.
About 0.2. Now, there's another thing I want to highlight. This graph, in terms of the graduations, you can't estimate 0.02 and all them something there. So for the most part, it is 0.1, 0.2, 0.25, 0.3. You with me? The graph does not allow you to give accuracy beyond that. So if I ask you for 15 and you tell me 0.28, me mark it wrong because you can't estimate that. Am I clear?
Yes, sir.
Yes, sir.
Right? So for the most part, this would be 0.25, right? 0.2? Yeah, we call it 0.2.
Sir,
Don't come tell me no 0.18. It's the fastest zero you will get.
Sir, could we tell you like a range in between X and Y?
Miss Michael, I say 0.2.
All right, sir.
Good.
Sir, now I understand, sir, you tell us to be very exact, sir. I know you tell us, you know.
What I am telling you is to listen to what I say and do what I say.
All right, sir.
Good. So moving right along. So I've just given you some values there, but I want to just run through an exercise with you. Yes. We are now 15 minutes. Wow. All right. Let's run through the exercise. So here it is. Here we have a network. And we are using overcurrent relay. So what you have there are maximum load current. You have the maximum fault current, and you have the minimum fault current. And these are values that we will use to set our relays. All right. So in essence, that lab that you did, the fault analysis, where you'd have to go through and you know your three-phase fault, you know your single-phase fault, etc., etc. These are things that you will do, students, in the real world. That's why I keep telling you, don't run through my labs as if it's just a computer exercise. It's something real. I don't just make up these things. Real. All right? Okay, so we have the information. The question is, how do I use this information in working with my overcurrent relay? Yeah? So we start. Are we ready? We have the information? Everybody?
Yes, sir.
All right. So we start by first step. We're going to select a CT that will not result in the relay operation for the maximum load. Now, part of this is that you are now going to select the top. Yes. And the main focus here is not on the CT. Even though, as an engineer, you would have to take note of the CT that you use. But for our purposes, we are going to give you the CT that you're going to use. You with me? So although I say select it, I'm saying no, I'll give that to you. So it's not something that you would have to worry about. But it's important from a protection standpoint that we do that analysis. But we're not going to do it today. So we're going to use a CT ratio of 100:5. 100:5. The RC that you see there, the RC equal 20, is just the 100/5. Right? That's the ratio. If you look back at the CT curves that I had given you, you would see that where they have, for example, the 1200/5, you would see 240:1. With me? So the 100:5, that will be equivalent to 20:1. So that's all that we are referring to when we say RC equal 20. So the first thing we want to do is to look at the maximum load, because you really don't want your relay to operate when the maximum load is being supplied. Okay, you want to supply the maximum load, right? I note, for example, when we did the lab number 1 and we were talking about how we go about correcting voltage issues, persons were giving me concluding statements to suggest that we remove some of the load from the system. You can't do that. How can you come and tell your customer that they must turn off them fridge? That don't make sense. You can't tell corporate Jamaica to turn off their ACs. I mean, if you have a national crisis, that's a different matter. But you can't tell the customer to remove their load for your voltage problems. So we have to correct it using different methods internally. But the point that we want to make here is that the system must operate while the maximum load is being supplied. So in setting your tap, you consider the maximum load. The maximum load is 90 amperes. So 90 over 20 gives us 4.5 amperes. So we want to next select the relay tap. We know that definition, okay? And the tap that you select must ensure that you can supply the maximum current. Everybody with me?
Yes, sir.
Yes, sir. Yes, sir.
Now the tap that you select will have to be based on what's available. Okay, you can't make up a tap, you know. You have to select what the relay has available. And we select the tap to be just higher than the maximum load. Because you can have a slight overload. There's nothing wrong with that. As I said, as I was explaining earlier, you may be doing switching operations and you transfer loads from one circuit to the next. But of course, that would not be there permanently. So you want to allow for slight overloads. So you select the tap to be just higher than the maximum load. In this instance, I'm going to select a tap of 5. Why am I selecting a tap of 5? Is because when I look at the output curves for the relay, these are the available taps. When I divided the 90 by 20, I get 4.5. So when I now come to the curve, I have 4. I can't select 4 because if 4 amperes come from the CT, yes, what that would mean is that the relay would operate when I want to supply my maximum load, which is 90 amperes. Is that clear? Talk to me.
Sir, go again, sir, please.
If I selected 4, what is the CT ratio?
4.5.
No, what's the CT? The CT ratio that we are using?
100
to 5. Good. So 4 amperes. If I have 4 amperes on the output of the CT, what is that saying about what's on the input on the primary side? If 4 amperes is coming on the output, how much is on the input?
Should be 80.
80. But what is my maximum load?
90.
90. So if I selected a tap of 4, what that means is that before I start supplying the maximum load, which is 90 amperes, the relay would start to operate.
Okay.
You with me?
Yes, sir.
Which is why we have to select the next best tap, which in this instance would be 5. All right? So that's why I select a tap of 5. Everybody with me now? So I'm going to now look at the minimum fault. So at the minimum fault was 350 amperes, yes? So for the minimum fault, with 350 amperes on the system, the CT, the current from the CT would be 350 over 20, which is 17.5. Everybody agree? But the 17.5, which is now the output of the CT, when I divide it by the tap, I get multiples of tap. And that multiples of tap is 3.5.
Sir, can I see step 2 for a second?
Hmm?
Can I see step 2 for a second, please, sir? Thank you, sir.
Welcome. All right. So we get 350 over 20, which is 17.5. So the multiple of top is 17.5 over 5, which is 3.5. So go to your curve now. Yes? If you go, everybody have a curve? We're looking at 3.5. If I'm using time dial 0.5, if I'm using time dial 0.5, what is the operating time for the minimum fault?
0.2, sir.
0.2.
And if I'm using time dial 1, what is the time for the minimum fault?
0.6.
All right. But because we are engineers, we use engineering notation, all right? So on time dial 0.5, it's 200 milliseconds. And on time dial 1, it is 600 milliseconds. Is that clear? Any questions?
Sir, that part they miss me, sir.
All right, we're going to give you a chance to do it again. So let us go to 1800, which is the maximum fault. So we know
Yes,
we know what 1800 amperes. Everybody, calculate for me the multiples of top. Everybody. So 1800 amperes is on the secondary, is on the primary. That's what's on the circuit. I have a CT, it's 100 to 5, and I have a top setting of 5. What's the multiple of top? Everybody calculate. I don't want you to show it out. All right. Miss Phillips. Miss Phillips.
Yes, sir.
Multiple of top.
Sir, I'm just calculating it. 1800 was the value that you gave?
Mm-hmm. So you get. If it's 1800 on the primary, what is the output of the CT? Phillips?
Sir, is that 90?
Come on, man. At this stage, you know, ask me that, man. What's the output of the CT, Miss Phillips?
So we're using 100 to 5, right?
Yes. What's the output? Huh? Not because I challenge you mean that you're wrong, you know. I challenge you because I want you to be confident in what you're saying.
So I'm still working on the confidence.
No, 1800 divided by 100 to 5. You don't need to be still working. What is the value? What's the CT output? Mr. Ramsey. Mr. Ramsey?
Yes, sir.
What's the output of the CT?
That is 90, sir.
90, thank you. So if the input to the relay is 90, what is the multiple of top?
That is 18, sir.
Thank you. So, Mr. Adams, if the multiple of top is 18, what is the output? What is the operating time on the 0.5 time dial? Mr. Adams?
Sir, you hear me, sir?
No, I'm hearing you now. Go ahead.
Sir, that look like 0.1, sir, 0.2. Sir, it says 0.
0.1.
Yes, sir.
Isn't it going in between the 1 and the 2, Mr. Adams? Or the 0 and the 1? We're at 18, you know. This is what we're looking at. We're at 18, right? And I'm asking you about 0.5.
Say the 0.5 curve, right?
Yes, that's what I said.
So 18 between the 16 and 20, sir. And on the 0.5 curve, sir, that's like 0.1 milliseconds, sir.
Okay. Anybody else? Anybody else seen anything different? For 18?
Sorry, 0.05.
Pardon?
And the 0.5 time scale, time dial setting, it'll be 0.05.
Which is 50 milliseconds.
Yes, sir. And on the 1, it will be 0.15.
Yeah.
Thank you. All right. So, Mr. Adams, I may need to lend you a pair of mine, okay? So it's 50 and 150 milliseconds. Any questions, students? Is there anything that I just went through that you're unclear about? Is there anything that I just went through with this exercise that you're unclear about? Okay. It is now 5 p.m. Tomorrow I have the first lab test at 6, right? So at the start of that lab test, I need you to complete the question 4, all of it, including the theoretical sections. All right? So I want to complete that question and submit it to Schoology by 6 p.m. tomorrow. So that's just the one question I want you to do for me. Everybody understand that?
So can you repeat that, sir?
Sir, question 4 from...
Question 4 from the paper I uploaded last week. Last year's exam paper. So I want you to do question 4. And please do your own work. Do your own work. Just for this once. Don't bother with the copying. Do your own work. And submit, upload that 6 o'clock tomorrow. All right. Now, it is 3 minutes after 5. If you have to leave, I understand. All right? If you have to leave, I understand. But to just complete the last couple of slides, I'm going to do that because it deals with the other protection. I have dealt with overcurrent. You know, we started out, we told you about magnitude measurement relays, then we told you about product measurement, and we told you about, well, ratio measurement, yes? So I've just looked at the magnitude, which is the overcurrent relay. So I just want to talk briefly about the some other relays. And if you have to leave, you pick up the information from the recording, but it's not a lot. Okay, folks? So whether or not you stay, I'm just going to continue talking because usually it's the same thing. I get the same silence. So I'll move on, all right? So as I said, I have no issue whether you want to leave the class. Okay, so differential protection. Now, differential protection, And we mentioned this last week about unit protection, that it looks on a distinct part or component or element within the system. Yes. And it will disconnect it for any internal fault error. And so there doesn't need to be any what we call coordination. Yes. In other words, as part of your protection system, and this, is something that we'll look at in more detail. As part of your protection system, there is coordination, meaning there is consultation with other parts of the network to ensure that our main objective is achieved, which is to keep as many customers connected as possible. All right. So with unit protection, you don't have to do that coordination. So if there's a fault on the equipment that is protected, you just separate. Okay. The system, however, when we're dealing with unit protection, we want to ensure that it remains in operation if there is what we refer to as a through fault. So in other words, let's think of a transformer. All the fault current that would pass through the transformer. If you think to the network that you built, I don't think, we did use some transformers there. Yeah. Excuse me. Based on where the fault was located, the fault current would have to pass from the generator through the transformer to the fault. Question is, objective, keep as many customers connected as possible. It means, therefore, that although the fault current passes through the transformer, the fault is not on the transformer. Yes? So you want to, the fault that you created in the lab exercise was on the line. So what you will want to do is to remove the line. But in removing the line, you still want the transformer to remain. That is what we are talking about here. So you can allow the current to pass through to the fault, but if the problem is on the piece of equipment you are protecting, then you want to remove it. All right. That said, one way of achieving that is differential protection. All right. And in terms of basic setup, this is what you have. You have your CT on one side, CT on the other side. This is what you are protecting. So that's the piece of equipment you are protecting. And this is our differential relay. The principle, we're not going to get into any math with this, but the principle is that the current flowing into the protected unit must be the same as the current leaving. All right. If that is true, if the current entering is equal to the current leaving, then it means that the fault is outside of the equipment that you are protecting, and therefore it should not trip. If there's a difference between the current coming in and the current leaving, yes, then the fault is on the unit and it should trip. Now I go back to that excellent question that Ms. Michael asked earlier, yes, regarding the harmonics. And what I was explaining about Inrush, from the operation of a transformer, and I use a transformer right? Because it is an excellent example. The operation of the transformer is such that you need to magnetize the core of the transformer before you have an output. So you have a current, you have a primary. That primary, if the transformer was de-energized, okay, that primary would have to energize the core as well as provide an output. Now, if you go back to what you did in machines, where we talk about, if you go through the cycles of magnetism, yeah, you remember the cycles of magnetism? Yes, where you draw your hysteresis loop, okay? One of the things that we speak about is the retentivity of a material, meaning the amount of residual magnetism when you have removed that input source, okay? So for your transformer, if you de-energize that transformer, depending on the retentivity of the material, the level of magnetism in the core may fall. So when you energize that transformer, part of the energy required, yes, or part of the energy supplied to the transformer would be used just to energize the core. Why am I going through all of this? Because this point that we are making here, for your differential system, it would see a current going in, but it will not see the corresponding current leaving, because the current going in is being used to remagnetize the core before you see an output. So what we do is to look at the harmonics that are present. So you have what are known as harmonic restraint coils. Yes. So it would detect the harmonics in the input current or in the primary current. And if certain harmonics are present, then it would restrain the differential relay from operating, because it would be saying to the relay, hey, there's an input, but there's no output. The input, however, it has these harmonics, and therefore it represents the magnetizing current or the inrush current. Okay? So this is true, but we have to bear in mind that the operation of our equipment has to be considered when making the final decisions. All right. So your differential protection, as I said, looks at current measurements and may be applied to your generators, your bus bars, your transformers, your feeders. And if you recall, when we were looking at the bus bar arrangements, we didn't go into detail about it, but we were restricted in terms of the type of protection that can be applied to your bus bar and based on the arrangement. You have two types of differential schemes. You have the circulating current, you have the balance voltage. The balance voltage is what we use for things like your feeders. The circulating current we use for generators, bus bars, and your transformers. Okay? In more detail, that's what we have here. So you have CT1, you have an output. CT2, you have an output. These two outputs are compared, and the difference gives you the relay current. That relay current, yes, beyond a certain preset value. All right, did you get all of this? I think I moved it a little quickly, but anyway, you can come back to the recording and get it. All right. Based on the preset value and some other considerations, it would cause the relay to operate. Okay, so just using some mathematics, nothing technical. If the circuit is healthy, it means that I1 is equal to I2. So in other words, if there's nothing wrong with what I am protecting, if the fault is outside, somewhere down the road, then whatever current is coming in would be the current leaving. Good. So if that is true, then I1 equal I2, which means that for the CTs, IS1 would be equal to IS2. Yes, and I suppose the big question in some person's mind is, but for the transformer, you know, how do we get IS1 equal IS2, given that the secondary current will be different in value from the primary current? That would be an excellent question. However, the CTs are connected in such a way that the same current would be seen as in terms of the output. So the turns ratio for the transformer is taken into consideration in selecting the turns for your CTs. Okay? All right. And so it means that IR is equal to 0. However, if we have a fault on the system, right? If there's a fault on the system, then the I1 would not be equal to I2, yes? And so IS1 would not be equal to IS2. And so IR would be greater than 0. Okay? And if IR is greater than 0 and it passes a certain threshold, then you have operation. Okay, students?
Sir,
And
in each, sir, quick question, sir. In each case, sir, for under fall conditions, sir, when I2 is not equal to I1 and IS1 is not equal to IS2, IR will be the difference of IS1 and IS2?
Yes.
Okay, sir.
Yes. But remember, although there's a difference, it has to be above a certain threshold. So it's not any difference. But if you want to hear more about this, I keep telling you, this is my favorite subject, protection, Networks 1 and 2, and these pale in comparison. Anyway, for distance protection, yes, once you have a three-phase fault, you're going to have a reduction in your voltage, and you're going to have an increase in your current. So therefore, the ratio of voltage to current will be reduced. Remember we spoke about the balance beam? Yes? So when you have the two coils exerting a force and they are equal, yes, that would be the set point. So the common point, or where constant, that will be a set point. And what we are saying, if you have a fault on the line, then your current increases, your voltage falls, and therefore that ratio gets smaller. All right? So the reverse is true for your distance relay as against your overcurrent. Because the overcurrent is that if the current exceeds a certain value, then it will trip. For your distance relay, yes, it means that if it is less than a certain value, then it will trip. All right, so that's the real, that's the difference in the principles. So what we are saying here, if the current increases by a factor of 5 while the voltage is reduced by a factor of 2, then the ratio would decrease by a factor of 10. All right? Which means that the impedance, which is what you're measuring, would be smaller. Okay? Don't stretch your mind over this. Just understand the basic principle. The principle is reduction in voltage, increase in current, which means reduction in impedance. And as I said, the principle here is that of an impedance relay. Yes. And in terms of the block regions, yeah. Please just add a D there. Defined by relay setting ZR. And this is based on the positive sequence values for your line. So just like what sometimes we do, we give you quite a bit of information, but of course it is the positive sequence value that you would need to consider. And then, so the relay will operate if and only if the voltage to current ratio is less than the relay setting. In other words, if Z is less than ZR, where ZR, of course, would be your setting. All right? Excuse me. The relay would therefore operate, yeah, You don't have to worry too much about this, but the characteristics is what I would have given you in the final figure. Yes, which is shown. All right. So ZR, this would be a setting impedance. Yes. And anywhere in this region. Yes. If you measure an impedance in this region, it will trip. So if the impedance is less than that ZR that you have set, your relay trips. Students, that's it from me. I think I have shared all that I can share on electric power systems. It has been an interesting semester. All right. You know, I know that the workload was no less than what would have occurred had we been meeting face to face. I trust that the information that has been shared with you, you will find it valuable and it will benefit you in your engineering careers. So to wrap this, we have that assignment I mentioned. I will put up the link and you can upload, remember, up to 6 p.m. tomorrow.
Finish.
You have your project, and of course on Wednesday we have the second lab test, Wednesday and Thursday. All right, so that's it from me.
Sir, question before you go, sir.
Yeah, man, go ahead.
In the scenario that we did earlier with our faults, was it a case that both for the 1800 and the 350 were working from the primary?
Yeah, man, that's what's on the system.
Oh, that's
so
I was a bit confused.
Okay, so yeah, so this would be what's on the system.
Okay.
All right. And that is what, remember what we said at the beginning, that these currents, once we exceed a certain value, we need the interface of a transducer.
Yes, sir.
All right, so that's the key. So that is what's on the system, and then the CT interfaces with the system and gives us an output. And then we treat with the output. In this case, we were looking at an overcurrent relay, but we'll also treat with that output whether we were looking at an impedance relay, et cetera, et cetera, et cetera. All right?
All right, sir. Thanks.
You're most welcome. All right. Anybody else? Any other question, comments, concerns?
So anything kind of pressure, sir, with the assignment and project review and lab test?
Mr. Smith, put it this way. You know, I hear that, but I put it to you this way. No, you know what? Let me leave it alone. But to the wise and to those who have been keen on taking note, you know, do the assignment. I run a democracy. You can choose to or not to do it. Huh?
Yes, sir. Thanks much regardless, sir. It's been an okay semester, yes.
Yeah. All right. Take care, everyone.
All right, sir. Take care.
Cool.